Electrolysis is the last topic in our electrochem unit, and electrolysis is the opposite of what we've been doing, okay? So what we've been doing is talking about what we call a galvanic cell, which is basically a battery. And a galvanic cell is a spontaneous process that produces electricity, okay? Electrolytic cell is the opposite. It requires electricity to run. So it has a negative cell potential. It is non-spontaneous. And so in order to make it to run, you have to put electricity into the cell. Okay? So what happens here, think about what happens when you charge your cell phone battery. You have to plug it into the wall. You have to put, send electricity through the cell phone in order to recharge the battery. And that's essentially what electrolysis is. Okay, it's making a non-spontaneous reaction happen by putting energy into the system. Okay, so the unit here is current. So when we talk about current, that tells us basically the amount of charge that's flowing per second. Okay, so current is measured in amperes or amps, and the unit is coulombs per second. And on our equation sheet, we have Faraday's constant, which is also coulombs per second. So that's going to come into play here. Okay, so here's a typical example of electrolysis. Okay, we want to know how much copper is plated out when a current of 10 amps is passed through a circuit for 30 minutes in a solution containing Cu plus 2. Okay, now plating talks, when we say plating, what we mean is we're meaning electroplating a metal. So you're causing the metal ions to form the solid on the surface of an object. Okay, so that's how you get electroplated things. You dip it into plating solution. Okay, so if you remember in our galvanic cell, the cathode always increases in mass. So that's kind of what we're trying to do here, is we're trying to make it go in the direction that will force these ions to form the solid on the electrode, okay? When you're talking about electroplating, typically we only worry about the reduction reaction. We don't write both half reactions because we only care about the one that's causing the metal to plate out of solution. So in this case, our half reaction is Cu plus 2 electrons gives you solid copper. All right, so back to our question. This is just a big stoichiometry question. So we're going to use a big, long set of train tracks here. So our starting number is 30 minutes. So that goes at the beginning. Now, amperes is coulombs per second. So our time unit has to be converted to seconds. Now we can convert that from seconds 30 minutes, and now we're going to multiply that by our 10 coulombs per second. Okay, so we start with 30 minutes, we change that to seconds, then we change seconds to coulombs by the current that's in there. Now we're going to use Faraday's constant. That's going to change from coulombs to moles of electrons. Okay, so Faraday's constant is on the equation sheet. Notice that we have to take care to make our units cancel. Okay, so now we have electrons. So we know that there's 2 moles of electrons for every 1 mole of copper. So that's our next step. So we use our mole ratio from the half reaction. The last thing we can do is multiply that by the molar mass of copper. And ta-da, you have it. Everything cancels out. And there's the mass of copper that we'll get after we run the cell for 30 minutes. Okay, let's try another one. This time we want to know how long it's going to take how long we have to run our cell at 5 amps to produce 10.5 grams of silver metal. Well, guess what? We're starting at the other end, but we're going to do a big long train tracks. So in this case, we're going to start with the mass of the silver. Okay, so we start with grams of silver. We're going to change from grams to moles using the molar mass of silver. Now we're going to change to moles of electrons. So we're going to use our mole ratio from the balanced equation. Every 1 mole of electrons produces 1 mole of silver. Okay, now we can take our coulombs constant and change that into coulombs, okay? And last but not least, we know that 5 amps is equal to 5 coulombs per second. So we use that to change to seconds. We want our final answer to be in minutes. So let's do that, and boom, 31.3 minutes. Okay, so these electroplating reaction calculations, really just a big, long set of train tracks, just a big dimensional analysis thing. Okay, now one other thing that comes up a lot in electrolysis is figuring out which reaction is going to happen first. Okay, so what you can do here is, so for example, if we have an electrolytic cell that has these 3 ions in it, it has copper, silver, and zinc ions, and we want to know at a low voltage which metal is going to be formed at the cathode. Okay, well, that's an interesting question. So we have to compare the standard reduction potentials. Okay, so what happens is that the more positive the reduction potential, the more the reaction has a tendency to proceed in the direction indicated. Okay, so in other words, the one that has the most positive value for its reduction potential is going to be the one that's the easiest to reduce. Okay, so Ag will go first, then copper, and then zinc. Okay, it goes right in order from the most positive reduction potential to the least positive reduction potential. Okay, and that's it. That is the end of our unit. Go ahead and try the practice problems that I posted with this assignment.